Hi, it's Victor Morganti here from FactEngine. We're looking at in front of us is some open source software that I've put together, and that's available on GitHub, and I'm hoping to work with members of the team to extend and solidify this piece of software cross-platform if possible, to make life easy for people to generate GQL schemas or advanced GQL schemas. Before I demonstrate this software, what I'd like to do is what we're saying with GQL is that we want graph query languages akin to OpenCipher and Cypher, so GQL, or part thereof, the graph side of things, to apply equally to relational databases. So what I'm going to do is I'm going to reverse engineer a relational database as a graph schema, populate it with the relationship labels, and demonstrate what can be done with that. Before I do that, let's have a look at where we want to go. So where we want to be is to have a relational database for which there is a property graph schema view over that relational database. Now we want a schema or a meter-meter model that allows us to visualize our data or database as, say, a relational database, and where we can have different views. So for instance, an object role modeling view, and so now we've got three views of our database as a property graph schema, a entity relationship diagram, or a object role model. And we're wanting more, so we want to be able to, for instance, have a look at perhaps a state transition diagram, say under the UML, and perhaps even other languages under the UML, say a use case diagram. So what I'm looking at here is a database for cinema bookings. So we have a cinema that has rows and seats are in sections, and we have sessions at that cinema, and where the session is for a film, and where a person can make a booking for a session, and that booking is for one or more seats. And we can have our typical graph database likes relationship, for instance, where a person likes a film and a film is liked by a person, and the person can like a film with a rating. So it's a real property graph schema where if I control click on, say, booking, I can see its properties, or person, for instance, so date of birth, login name, age, that sort of thing. We've got a property graph schema over the top of our entity relationship diagram, for which we have views of a object role model that's not showing at the moment, or a state transition diagram, or other UML type diagrams, so a use case diagram where a person makes a booking for a session by phone, where they call the cinema, they select a session, they select a seat, and then they confirm their seat booking, etc. Now all of this is achieved under one schema, so one meter model. inside this piece of software, which is Boston by FactEngine. Now, to get there, we need our schema in the first place. So let's jump back to, say, the piece of software that I've put together as a demonstrator. And if we import a schema directly from a database, so I'm going to do this from a SQLite database, and I'm going to select my Cinema Bookings database and give that a second to do its reverse engineering. I'll end up with a second schema here, cinemabookings.db, where we've got our node types, so booking, cinema, film, person, row, seat, section and session, with their various properties. So a session has the properties of a film ID, a date, time and a cinema ID, etc. A person, the person ID and login name. I haven't got age or other properties on this particular database. Now, the relationships, when it reverse engineers, I've formulated under the research and development of this the ability to automatically detect what are the edge types within a property graph schema for a relational database. They're all set to has because we need to provide the predicates for the edge type labels. So a booking, we'll just set that, is for a person. A booking is for a session. A film is showing at a cinema. Now this film is showing at a cinema is actually our session node type. So film showing at a cinema on a date time, and where date time is a value type rather than a node type. And as you know, in a graph database we have a choice at the property graph schema level of showing a node type, so a round circle, and even within the implementation of a graph database, having a node type or an edge type with a property on it. So this film is showing at cinema would have a property of date time. So it's not showing that property at this stage, but you get the picture. So this edge type actually exists within the relational database, even though it's a table within the database with these three columns. We can still query on film is showing at cinema. So let's quickly just finish these, and then we'll talk about some more serious concerns. So person booked. So person booked a session, which in the same way is booking. So a booking is where a person booked a session with, say, a derived seat count, and session is film ID, date, time and cinema. And don't forget, we're looking at a relational database here. So a row is in a cinema, a seat is in a row, a seat is in a section, so like gala or public or deluxe section, something like that. So seat is in a section, and a session is for a film, and a session is at a cinema, and we said that a person likes a film with a rating. So if we look at the properties there, we've got a person ID, a film ID, and a rating. And a booking has one or more seats, and where that's a many-to-many relationship. So we've got our property graph schema in tabular format, and we can export that as a graph schema JSON. I won't demonstrate that, so I've got it generating the Neo4j, I think it's still in beta JSON format. The GQL various working groups may come up JSON or XML format for that, or as a fact-based model in XML. Now, fact-based modeling file or fact-based modeling in this context means the meta model of object role modeling. So we're going to we could store, I'm not going to do it because I've already got it imported into Boston, a meta model or a meta model, depending how you look at it, of this schema as the meta model of an object role model, and in XML. So this piece of software is open source. The licensing on it is that free to use, but you're not allowed to build a competing product to Boston with the DLL that it uses, which is called FactEngine for services.dll. That's proprietary and a saleable product of FactEngine. At the same time, I'm happy to provide insight, be a fly on a wall, or provide thought leadership in this area as you need me. And let's have a look at where this relates to actually querying databases as well. To Boston now, and we've already seen that we have, I'll just close that main form and reopen it. We can import a fact-based model, which is the XML object role model, as a meta model or meta model, to get the schema that we just created, which is this property graph schema here, and we can visualize that as a entity relationship diagram, because we know we're looking at a SQLite database, and this model here has the SQLite database logo, SQLite logo associated with it, and we can have other languages under the exact same meta model. So there are multiple meta models, but I'll describe how that works. We have one meta model, which is the meta model of object role modeling, and we can have state transition diagrams. Please forgive these images that have popped up there. A use case diagram, property graph schema, or our object role model. Now, object role modeling is very useful because it provides predicates that can be used in our entity relationship diagram and for natural language queries. So, for instance, a seat is in a row, and a row contains a seat. Now, that's not a edge type label, the same as the way it's done mostly with Neo4j and other graph databases in capitals with underscores, is in. But if I click on that, we'll see the is in and contains where a seat is in a row and a row contains a seat, and we'll see soon how that helps with natural language queries, which comes in very useful for, say, artificial intelligence and doing graph RAG, retrieval augmented generation, etc. So those predicates carry over also to our entity relationship diagram, where if we've got a stylized Barker type entity relationship diagram where we've got predicates on our relationships between entities, we've got seat is in row and row contains seat, which comes from our object role model. Seat is in row and row contains a seat, and what we're doing is, if I go to the properties of that, we're also adding a what I call a graph label is in that sits on top of that fact type. So if you've done any work with yarn headers, you'd be familiar with object role modeling. This is the fact type, and we can associate a graph label with fact types to be able to do our property graph schema in a format that is familiar to everyone, say, who's working with, say, Neo4j or other well-known graph databases, and has become a standard to use this sort of shorthand form. If we wanted to provide true thought leadership, we'd move 100% to object role modeling and have reciprocal predicates where we can do our query saying which row contains which seat, in as much as we can say seat is in row. So before we move on, node types can be fact types themselves, special types of fact types, where booking is a fact type where a person booked a session that have been objectified, and so too you can have a graph label on, let me just click on that, we haven't got that there, on our node types, which are objectified fact types as well. Why you would move to object role modeling is because there's a serious problem when you're object role modeling as a meter-meter model, is because there's a serious problem when you have two concepts rolled into one. You've got this thing called session linked to cinema, but we also need an edge type where we're saying a session is at a cinema. So we're not just saying film is showing on date time at a cinema, we're also saying that a session, so when we objectify this fact type as a node type in our property graph schema, we can say that a session is at a cinema. And if I look at the graph label for that, I should see an is at label. So is at in capitals with an underscore, as is common with property graph schemas, and it's this is at graph label relates to a very special thing in object role modeling, which is a link fact type, which allows you to not only see these edge types here, but also relationship types or relationships in our entity relationship diagram. I'll briefly show the power of this when it comes to GQL by actually using FactEngine. So if I go to FactEngine and write a simple query in natural language, so I'm going to say which seat is in which row, that gets translated to FactEngine query language, via a large language model, which is pretty much the same query, which seed is in which row, and we get our results here. The query, you might think, okay, well, it's SQL because it's an SQL-like database. But what we want with GQL is to be able to say, well, actually I want a GQL, like an open cipher query, that if I wanted to write something more complex, such as show me all the seats in the public section, and I say that I want that in open cipher, I now have a query which is in, say, GQL or open cipher or cipher with a match clause, a where clause, a return clause, etc. I've got my results, and what's happened behind the scenes is that that's actually been translated into a SQL query with a, in this case, an open cipher transpiler. Quite a long query with this transpiler, such that the actual query run against the database is in SQL. The query we ran was either GQL, open cipher, cipher, and we've got our results from a query against a relational database. So in this instance here, we've actually got 4 query languages all over the one database, which is a relational database. We've got natural language, which we could be using for, say, retrieval augmented generation from a AI large language model, translated into FactEngine query language, which seed is in the section public, translated into, say, open cipher, if that's what we want, or GQL. But we know our database is in SQL, so we translate it to SQL, unless someone implements GQL by default within the implementation of the database. But if you want to get up and going pretty quickly in the next couple of months, you'd implement something like this. And we've got our results. So 1, 2, 3, 4 languages. So natural language, FactEngine query language, the language that we're querying the database, and then the actual language that is run against the database to get our results. This isn't a plug for FactEngine query language because we're focused on GQL, but you could just to demonstrate the sort of thing that we're working with, I could say which person booked a session that is to watch the film Grease. And hit go on that, and we've got Paul and Peter. We've got a query in SQL, having changed this back to SQL to get our results. So how does all this hang together? Well, it actually has a 4-layer architecture. So as a heads up, it's a 4-layer architecture where we have a object role modeling meter model as either a meter model or a meter model, so an M3 and an M2 layer of a OMG object management group, 4-layer architecture under the MOF, say, and as used for XMI. We've got an M1 layer, which is the meter model of the various languages, so object role modeling, entity relationship diagram, use case diagram, say a event trace diagram, say a data flow diagram, and this can be used for shackle. There's no problems there because object role modeling has a lot of constraints, etc. And then underneath that you've got your M0, which is your data layer. So I call that the Richmond architecture, which is a classic 4-layer architecture. So you have a meter model and a meter model rolled into one, and it just depends on how you use that, and I'll show you that in a second. Then you've got your model layer, so your actual models that we're looking at on the screen, and then your instance layer, which is your data in your database. Now under the MOF they draw it this way, so you've got your M3 meter model, M2 meter model, M1 model, and M0 your actual data. In Boston, or the particular proposed use of object role modeling as a combined meter model, we have an M3, M2, M1 and 0 layer, where when the same model, so we can use the same model as both meter model and model, and meter model and meter model. For object role modeling models, it becomes just a meter model, and we view object role models. But if we were, say, talking about a state transition diagram here in the lower right hand side, you can store your data for this model within a meter model as an object role model, which can be stored at the highest level as an object role model, this object role model with data, treating the M3 layer, so the schema that we generated from the new tool that I've put together, as a object role modeling meter model, and M0 is our ultimate data layer within our database. So I'll demonstrate how that works inside Boston itself. Now, if you can imagine, Boston is built on the meter model of object role modeling, so it does object role models by default. So we've got this scenario. We've got the database or the XML of a model as an M3 layer as a meter model, treating it that way in this instance, or it could be, we could draw it down here as M2 if we wanted to, our object role model, and then actual data. So this is stored in this model as a meter model. This is the model, and I can look at the actual data. So for instance, if I right click on row and view the table data, we can look at the actual data in the database down here, down the bottom, and that's our M0 layer. So M0 layer, let's say an M1 layer, and then the actual model stored as XML or in the database as a meter model. Now that exact same meter model can act as a meter model, that if I look at a straight state transition diagram where we're looking at the film screening status of a film, which if I go to this film object role model, so film has a film screening status of pre-screening, screening or no longer screening, and I'll go to its state transition diagram, I can see that we start at pre-screening, we go to screening, then no longer screening, then end. But if I look at the meter model behind this model, I actually look at a object role model, and this is the meter model of that state transition diagram. And if I'm lucky, I should be able to right click on this and view the fact table and have a look at the actual data that's being used to draw this state transition diagram. So this meter model stores data within the object role model, and it's stored, if I look on the left hand side here, in my cinema bookings XML, used as a meter model for all these different languages, for natural language queries, for GQL OpenCipher queries, or SQL queries, or Shackle, or whatever we want. Now that's our 4-layer architecture. So when we're looking at object role models, we're looking at 3 layers, with object role modeling meter model as a meter model. When we look at, say, a state transition diagram or a UML diagram, we have a 4-layer architecture, and which is we don't need to reinvent the wheel. This sort of technology has been around for a long time now. This is a picture for the OMG's MOF, and similarly for the OMG MOF, and as used with XMI, etc. And I call that the Richmond Architecture. So I'm happy to provide any thought leadership that's required in this area. The only plug I'll make is that I am available and happy to provide consulting, and I can't wait to do more work in this area. Thank you very much.